Welcome once again to our online reinforced concrete design training. Now we'll be talking about slab design. Slab design. Normally, for structural design, what we see is the architectural drawings. That is what we see. The first thing we get to when we design the structure, and we'll just use this typical one that we're seeing here. A typical one. If you have your slab arrangements anyhow you want it, but there's a principle I want us to understand. We have on our slab design, we have one-way slab design and two-way slab design. One-way slab design and two-way slab design. How do you determine, or how do you know that your slab is a one-way design, or one-way slab, or the other one a two-way slab? A very quick one would be the length over the breadth, as in the long span divided by the short span. If it's greater than 2, then you know it's a one-way slab, or if it's less than 2, then you know it's a two-way slab. So looking at typical example here, let's consider this our slab here. If you look at the long span over here, which we have 4 meters and 3 meters plus 3 meters, making it 7 meters long, then our short span over here is 2 meters. So if you now divide 7 by 2, you get 3.5, which is bigger or greater than 2. So we can comfortably say this our slab is a one-way slab. So what's the difference between a one-way slab? The one-way slab, your main reinforcement runs between parallel to the short span. If you look at the direction of this arrow, shows your span, how your reinforcement will run on your slab. Then this other part will just be the distribution bars. But for your two-way slab, how do you determine the two-way slab? Now we are having 5 divided by 4, we have 1.25. If you now say, okay, try this other, if we now try this other panel, if we try this other panel, which is 5 divided by 3, we have 1.66667. Or whatever one we try, it shows that your answer is less than 2, so it makes it a two-way slab. So you are reinforcing on both direction. So now, if you've determined that, the next thing you need to do is, how do you size your slab? Okay, I will tell you how you can size your slab. A quick one, what I normally do is, if you look for the short span, you size your slab using, in a slab, you use the short span to size your slab. And one of my rule of thumb is, if you consider all the panels, look for a panel that has the largest short span. And if you look at this one has the short span here is 4, while the short span here is 3. So I will use 4 to determine my size. Now, right now, maybe you don't know what will be the thickness, because it's the work of the structural engineer to determine how thick your slab should be. And now the architect has finished his work and is now waiting for you to determine how thick your slab is. So your go-to way in sizing the slab is consider the short span, the largest short span, and we'll proceed from there. Okay, so this is our slab design. This is our slab design. So the preliminary sizing, the formula says the minimum, as in the minimum effective depth of that slab, must be greater or equal to your span, which is, now we are saying the short span that we are considering, over the basic ratio multiplied by modification factor. And please note, our modification factors for different supports, different slab, it varies. For continuous slab, it is 26. For simply support slab, it is 20, and for cantilever slab, it is 7. So with this, and now we know from our drawing, we know that it's a continuous slab. It's not just a one slab. So we'll be considering 26. Then the modification factor, well, there are other factors, they've done it. So, but what we are considering is 1.38. Our span, we said, is 4,000 mm, 4 meters or 4,000 mm. So the minimum must be greater than 4,000, which is our span, divided by 26 times 1.38. So we are having 111.1 meter as the minimum. So in order for us to estimate the depth, the total thickness of our slab, H will now be minimum, the minimum, plus our concrete cover, which is the concrete cover, then plus half of the reinforcements that we'll be using, because the effective depth takes from the top of our slab or the top of our element to the midpoint of our bars, our reinforcement. So if we consider that we have 111.1 plus 25, which is our concrete cover, plus we are using the 12 mm diameter bars for our slab. So divided by 2, if you add up all of them, it will give you 142.11 millimeter. So with that, you try H as 150 mm. So, but if you have something bigger than 150, the next one we consider is 175. So we've sized our slab and we have 150. So after that, we can now do our moment. Like what I said earlier, you can either do your movements manually or with computer. So either which one is okay. But for now, we are considering a simply support slab. If you have a simply support slab, we consider the formula says WL square over 8, where W is okay, WL square over 8. Okay, so with that, WL square over 8. So in later time we will explain further on how this 10.24 came about. So now after we've achieved our moment, the formula that we've shown before, K equals to M over FCUBD, where you now factor all this to determine our K. So the B here for the slab is considered 1 meter, slab of 1 meter. So that's our B. So after factoring everything, we have 0.05. factor it into later on the formula, and we have LA as 0.94. So the AS required is equals to moments over moments over moments over 0.95 times LA multiplied by D. So if we multiply that, we have 465.1 mm square. 465.1 mm square. So with this we can now estimate. We now estimate or check to see the numbers of reinforcement we need. Okay, if you look at the loads, that the area of the steel required is 465.1. So what do? We go to our table to pick the one closest. If you look at this is the area for bar spacing. We have slab, we have wall, we have pad footing. This is the table we use to determine that. So we are picking diameter 12 for bars, and now in diameter 12, if you trace down to 465.1, is closest to this, but is above. So the next one closer, a bit above it, will be this one. So we can now choose Y12 at 225, which will now be the area provided. Area provided will be 502 millimeters. So with this, but I said something earlier. How did we achieve this 10.25? So if we do that, how we achieve it, we can see from below. Like what we earlier discussed is the self-weight of the slab. To determine the self-weight, we have 150 of the thickness of the slab, which is 0.15 times the specific weight of concrete, which is 24, to give us 3.6 kilonewton per meter square. We are finishing, as in 50 mm thick finishing on the slab, which is now 0.05 times 24. We have 1.2 kilonewton. So partial load, the table is the chairs, the whatever, the partitions that will be on the slab, let's say 1 kilonewton per meter square. So the total of what we have, the total characteristic dead load will be 5.8 kilonewton per meters square. So of our life, the gross load, the characteristic life load for, they have different code for general use. The domestic use we say 1.5 kilonewton per meter square. So our design load, factor load, which will now give us 1.4 GK plus 1.6 QK. If we put all into this formula, I get 10.24 kilonewton per meter square. So that is how the 10.24 kilonewton came about. So with this, if you've done that, then you've done your design for your slab. So if there's any question, you can ask the question.